Hey guys, welcome back to the channel. Today I'm going to start building something I'm very excited about, a Segway. Now I have a few goals for this Segway. First and foremost is that I want to keep it low cost. I don't want it to be something that if you decide you want to build, you have to shell out an arm and a leg for. The second thing is that I would like to make it as open source as possible. I want to do the software and hardware with full release plans and documentation. And the last goal is something that I think will really put it over the edge. I want to incorporate a level of robotics that I haven't seen in other self-balancing or personal drive vehicles. I want to add SLAM. SLAM stands for Simultaneous Localization and Mapping. And what it does, it's the system that allows robots to navigate their environment. It's the same methodology that if you have a Roomba, it's using to navigate your home. Now this is going to be a multi-step process. So this is just the first video of several others. In this video, I want to discuss what it's going to look like and the parts I'll be using to construct it. First and foremost is the drive. How will I be moving the vehicle back and forth? What do those motors look like? Well, they're going to be using the hoverboard motors. Hoverboard was mass manufactured, and as a consequence of that, their motors are extremely cheap for their torque curve. Basically, if you were to get the same motor at the same torque that wasn't a hoverboard motor, you'd be spending significantly more money. I got a set of 2 of these for I think $60, and that's what we'll be using. These are really tiny wheels though. I don't want my Segway to be sitting this low to the ground. That's not going to be very fun, and honestly I just don't think it looks that cool. So what I did is I went out and got 10-inch tires. These are just regular old tires off Amazon, link will be in the description, that you use for maybe your wheelbarrow or some other equipment. And we're going to modify those by basically drilling into the back side of the motor, or the front side, if it's looking at you like this, and attaching to the existing mounting holes on this wheel. And that'll be a future video. Then for the actual robotics aspect, that's where I'm most excited. We'll be doing a couple things. First and foremost is that we need a processor to handle all of the robotics side of things. So SLAM is fairly computationally heavy, so you can't just use any off-the-shelf board, but it's also not so crazy that you need to jump straight to plugging in a $2,000 laptop and driving around with that. So what I'll be using is a board from Pine64. Again, linked in the description. I absolutely love this company. Pine64 has done an incredible job making single board computers not just accessible, but also they'd make them open source. They've added in a huge community for operating system development, program development, and they're just really fun to work with. I've emailed them directly for other products with questions, and they get right back to you. They want to support you, and they get really excited about what you're building. So check them out, give them some love. But we're going to be doing this on one of their Pro board, and I'll get to the exact details in the description. Now this board is going to allow us to run the operating system that we'll be developing. We're going to be doing that with a project called Yocto, so we're building our own operating system. And then also support the software packages to drive 2 primary sensors. Now that software package is going to be ROS. I'm going to be using the robot operating system, which despite its name is not actually an operating system. It's simply a tool used in a lot of robotics to do get you up and running very quickly with things like SLAM or sensor configurations, all those types of things. It's got a great simulator, so we'll be diving into that in some future videos. I'm very excited about that. Now the 2 sensors I'll be using are this Lidar. This Lidar is the Sweep Lidar, and it's a super low cost and very, very easy to use little simple Lidar system. It plugs directly into the ROS software stack, and within about 4 clicks you can get live data feeding out to your console. It's fantastically awesome. I love it. It's super cool. I'm not actually sure about their long-term support, or if you can still buy a bunch of them, or if it's kind of just find the ones that are out there in the market. I do have one that I'm going to be using. If not, any Lidar will work. You're just going to have to build into the ROS software stack support for it. But in the future videos, I'll be covering a lot of that, so you should be able to pretty much take any Lidar that you have. The other thing is I'm going to be using an Intel RealSense camera. Intel RealSense's entire product line is fantastic. I'm really familiar with their D435s. Those have depth IR, near IR, and RGB built right into them. This camera right here that I'll be using is the T265 tracking camera. Now the difference with this camera versus one of their other Intel lines is that this one has a built-in IMU. And an IMU is going to give you positional information about your robot. So it's going to tell you how you're oriented, and how fast you're moving in either axes. This is critical information when you want to have a very precise SLAM system running and navigating a robot. There's several ways to do SLAM, which I'll get into in the future video, but we're going to be using visual odometry, ICP point cloud, being informed by an IMU. All of this is going to be built in ROS and honestly is pretty much built for us at this point. All we have to do is plug in the right sensors and configure it properly. All of this being said, I'm hoping to have a robot that will map the entire room. We're going to map this office space that I'm in, and we're going to have it autonomously drive to us. I would like for the system to be able to navigate around the environment, me sitting at my desk and decide, you know what, I'm feeling kind of lazy. I don't want to walk to get coffee. So instead, I'm going to summon it, and I'm going to hop on it and drive it to the coffee. That is the end goal. If we get to that, I will be super happy. But baby steps. First and foremost is we have to build it. So that being said, let's go jump into FreeCAD, and I'll show you the design for the Segway. Alrighty, so we are in FreeCAD, and we have the full assembly right here. So what you have is basically two parts. You've got the kind of base module, which is going to be all the electronics, the battery, the drive motor, which I'll get into in a second here. Then you've got this kind of handlebar. Now, the key to take away with this is looking at it, first off, everything was done with hopefully off-the-shelf components. I wanted to make sure that anyone could buy these parts with really no limitation on access. So everything's done with either 3060 aluminum extrusion or 2020 aluminum extrusion. For the actual handlebar assembly, it's 2020 aluminum extrusion. So first thing you'll notice on the handlebar assembly is the actual Lidar. So if we take a look here, it's the sweep Lidar, which I mentioned earlier. And it's super easy to use with multiple different software packages. The one we'll be using, obviously, is the ROS software navigation stack. And it is just basically plug and play, about 4 clicks, gets you up and running. Highly encourage you to take a look at this. I'm not actually sure about their current availability, given this is kind of an old Kickstarter and where you can actually buy them. But I'll leave a link in the description below for this site, and you can take a look at their videos and maybe get one for yourself to play with. They're really exciting. Then moving up the chain, we've got the Intel RealSense camera. Now this is the depth camera that also incorporates an IMU for tracking. The site itself, again, leave a link. A bunch of different varieties of cameras. They even got their own LiDAR system. This one, though, in particular, offers onboard SLAM if we want to try that. So I want to incorporate a system that has redundancy for the Segway, and I think using its onboard SLAM might be a cool feature set in addition to the raw SLAM. You'll notice that I put it up top where the actual hands would go for the handlebar. The reason for this is really just the field of view. I want to make sure that as I move forward, I have a really good full view of my environment that I can do some more computer vision stuff with. I've got a few ideas for how I want to use this entire robotic platform beyond just the SLAM approach. And having it up top is really going to help a lot. Some systems will have cameras down at the ground, and this is if you have really precise requirements on collision, or if you want to make sure that you're not falling off a step or a curb. For me, I'm willing to take some of the sacrifice of that inherent risk to actually have a better understanding of my overall farther out surroundings, particularly with the computer vision approaches for things like line detections, or if I want to run some machine learning on this guy, it'll be fun to have it there. Circling back to position on the LiDAR, you'll notice that I had it kind of at halfway up the handlebar. This is important because when I actually do the SLAM, I'm going to have to build a map. And in building the map, if I had it too close to the ground, I'm really only covering the top, I don't know, maybe foot of actual environment. And that can be fairly dynamic. Oftentimes you have chairs, table legs, people even in that area. By having it farther up, ideally, I'm hitting kind of midsection on the wall, which should be a far more stable and static environment to map. That being said, since I'm using aluminum extrusion, I designed this system to be adjustable. If I want to move the height of either of these sensors, the only thing I should have to do is unscrew these and lift them up or down, and then just adjust their position in the transformation config, which will live on the ROS stack, so that the actual computer and ROS knows where the sensors actually exist relative to the Segway sensor. If we actually now go to the base assembly, which is really the meat and potatoes of this entire project, start breaking this down kind of piece by piece. The first thing you'll notice is I've got a representation of that 10-inch wheel. So this guy actually is what will mount on top of the hoverboard motor. The hoverboard motor you can see here is a representation without its tire, and the actual construction of these in real life will be in a future video where I show you drilling through the actual frame right here, or rather the casing, and attaching that larger motor. And then while we're at the motor, really one of the more critical parts that I want to highlight is the fact that I've got this motor mount situation going on here. Now this motor mount, I don't have a mill. I don't have a mill that can actually mill these guys in these unique shapes. So instead what I'm going to try printing these with high density. Now I really don't have high hopes for that. I kind of anticipate that it will break and fail, and I'll be having to redesign a motor mount that I'll actually be able to mill. That's my assumption. But because I already designed this, and if I can keep it without having to use a CNC, it'd be more accessible to people, I'm going to give it a shot. So either it works and you see success, or it fails and you'll see it fail. Either way, you will see the end result. I did run on this guy a actual simulation, and you can see I basically simulated the Newton forces going down and going up on the motor of an average person, specifically my weight, and you can see it actually deforms a lot. This is with ABS as the material choice. So I'm assuming that it's going to break, and then I'm going to have some issues, because you can see on the deformation there, depending on how I print it, it will likely shatter the actual print lines, as opposed to just deforming the way it assumes a solid chunk of plastic would. But either way, we'll give it a shot. So moving on to the next thing is this battery. And so right here, what you'll see is a representation of the battery I'll be building, which is a 10S 4P battery. It's going to be constructed with the battery kit from this place right here, who I'm not even going to try to pronounce their name for. The really cool part about this kit is that it's solderless and tack weldless, so you don't actually need to have any equipment to construct your battery pack. They're all go together with, as you can see here, kind of these screw terminals. In addition to these plastic pieces and screw terminals, you can also get the battery management system and some heat shrink covering to keep it all protected from the elements, which is going to be really nice. I'm going to put it in an actual project enclosure as well, but the construction of this will be in a future video, and I'm very excited about that. That's going to make it way easier to do the electronics. So if I remove that, the next thing you'll actually see is I've got this kind of top plate. And you notice it's transparent. That's intentional. What my game plan with this guy is to actually do a plexiglass cutout on a laser cutter, and hopefully that'll support the weight. I've got these support rods here. These are 2020 extrusion, just feeding into the 3060. Nothing fancy there. If you ever done a 3D printer or anything like that, this will be a pretty similar technique in construction. But the idea is that I really want something that you could actually see what's going on. I wanted to make this something visually appealing, and I think by having it transparent, I'm going to accomplish that. As long as it can support the weight of standing on it, I think we'll be in good shape. If I go ahead and remove this, we can get down into it a little deeper. Like I said, we've got this 2020 extrusion support, and actually below that, if I kind of do a top view, I've actually got 4 main electronics in here. The first being this Odrive, which I kind of mentioned a little bit earlier. Odrive is an open source brushless motor controller. This thing is insane. For its price, I haven't found even a remote competitor. It lets you do 4 different types of control. You either have a go-to position, which is pretty much doing trajectory planning, or you have just kind of a dummy position command, velocity command, or torque command. For us, we'll be doing velocity, obviously, as a Segway is essentially just a vehicle that balances, trying to keep the center point underneath itself through different velocities, either forward or backwards. One of the exceedingly cool parts about this is its multiple control interfaces. I'm going to ideally be using the CAN interface, and this interface lets you do a whole bunch of connections on essentially a single bus. It's what your cars use, and it is super popular. When done right, super stable. If that fails, if I have some complications with that, I will probably default back to UART or USB. Super simple. This single board can drive 2 motors, as it shows here. I think each one has a peak of 120 amps. Yes. And I think a stable of about 40, which is well within the range of the hoverboard motor. Come back over here, we've got a regular Arduino. This Arduino is really just there to support the Adafruit IMU. I'll put a link in the description below for the exact model I'm using. This board is actually super off the shelf and super common. Really nice board, very good results for how cheap it is. And the main point of this IMU is to actually support the PID loop that will process the self-balancing algorithm. That guy, I'm also hoping to incorporate his IMU feed into the SLAM navigation stack in addition to the Intel RealSense's IMU. It's always good to have more sensor data rather than less, and if I can incorporate both of these perhaps through a Kalman filter, I think I'm going to get really significantly good results as opposed to if I just did a single one down here. And the last and final is the actual brains of the operation. This is the Pine 64, specifically the Rock Pro 64. Now, Pine 64, as I mentioned earlier, is this amazing company that offers a whole bunch of different devices. You can see here, they've got a huge selection of single board computers. They also do laptops, phones. They have an awesome smartwatch, which runs FreeRTOS, which is a real-time operating system. And it partners with a GUI on top of that to actually have a really cool, I think it's $25 smartwatch. I've got a project working on that guy that's going to be a future video. So if you want to see more about this, make sure you subscribe so you can get notified when that actually comes out. They also do little compute modules, and they even support like a cluster board, soldering irons. This company is insane. The reason I'm going with the Rock Pro is I've got a couple of them, and I've kind of stress tested them to see that they could actually support what we're trying to do here. You can see some of their kind of overall specs with their processor, the RAM, and the actual different kind of interfaces. They do run eMMC, which is cool. That's what we're going to use to boot as opposed to SD. If you look at some of the other devices, they kind of all vary, mainly just on their processor and some of their RAM. So this A64 LTS is one I have a bunch of. And you can notice it's got 2 GB RAM. It's a different processor, A64. It's an amazing computer, and honestly, as soon as I found them, I moved away from Raspberry Pi. They will do just about everything. They also support, very easily, the Yocto Project. And the Yocto Project is what we're going to be using to develop our operating system. Yocto Project is what's used to make your own custom embedded operating system built on Linux. So essentially like a flavor of Linux. It lets you take the kernel and then manually add in very specific and very fine-grained projects or applications that you would want. So you have this ability to have a very optimized operating system and have built-in support for the things you want. It also, in the build process, produces an SDK. So if we write any of our stuff in, say, C++, we need to be able to cross-compile to our architecture. It will provide us with an SDK that we just need to source and run CMake with, and it'll be up and running on that processor. One of the things we're going to do is add what's called the ROS layer. The ROS layer is essentially a pre-built support package that basically will install ROS on your operating system from the get-go. And for us, that's going to be super important because you don't want to go through the process of installing ROS on the embedded architecture after the fact, because essentially you're going to be downloading SSH from the board, download, compile, all that. This way, if we add it through the actual compilation of the operating system, from the moment we boot, it will be there ready to go. So that's super exciting. It's going to be a great feature set that I'm very excited about to kind of dive into and show you guys. It's really cool. This entire project is just fantastic. And then you've got the base plate. The only other cool thing about the base plate is that it is designed to support, it's going to be plexiglass, and then all the hole mounting is done with just threaded inserts. So there'll be melt-in threaded inserts, I think supporting 2.5 millimeter screws. The idea here is that I think I've gotten this layout pretty much how I want it, but anything on this entire platform, whether it's the handlebars or the actual mounting of the rails, I wanted to make sure that I could adjust on the go or make more customized as I add more features and really just find new uses for the robotic platform that currently is going to be a Segway, but could be much, much more. The idea is that I could just either take it to a drill press or manually drill out holes that are the rough diameter of the threaded inserts without having to be perfect, and then just melt them in like I normally would. Yeah, so with that said, the only other thing is let's take a look here at just some of the aluminum extrusion. I'll be getting this from 8020.net. It's a super great supplier, really cheap for a lot of this stuff. I'll be using standard 2020, then I've got some L bracket. Everything's going to be put together with T-nuts. I'll be using, I think those are 6 millimeters screws. Then I've got the T-bracket for the conversion from 30 millimeter to the 20 millimeter handlebar. A couple angle pieces, those are used for the actual support 2020. And then really just the 3060. You can see kind of it's nothing super expensive. You can really customize on length, so I can get just exactly what I want. I'm pretty excited about all of this. It's going to be a really fun project. So the idea of this entire system is that it's modular. I really want to make sure that if you wanted to work on it, you didn't have to go out of your way to take it like half apart or all the way apart to work on the electronics, adjust the wiring, change software, any of that. I really believe that you shouldn't sacrifice spacing for workability of the components. I've been involved with a few projects like that where basically you try to get everything really compact, but it hurts you if you ever have to take it apart and work on it. A perfect example is like the iPhone, right? You have this super compact, really awesome system, but if you ever try to get in there and actually work on anything, it's going to be a nightmare. For something like this, especially an independent project, I really believe that you should just give yourself more space than you think you'll ever need because you'll probably fill it up. So if you actually take a look here at the assembly, if I kind of run the exploded view on this guy, what you'll see is kind of how I expect it to come together and take apart. Everything should be separate. One of the big keys is that if you take this top plate off, the goal is that you have full access to all the electronics. This motor connector, along with on the handlebar, the actual Lidar, and the RealSense camera, I plan on having all feed to essentially a central connector hub. This connector hub is going to live on the actual base plate, and then from there get wired to all this correct electronics and correct boards. That means that if I wanted to just take this entire bottom plate out and work on the electronics individually, I should be able to. I should be able to have this completely separate from the system and have it go together super easily without having to take apart the entire rest of the Segway. That is going to let me dev in cycles. I'm not going to have to get everything done right away as I put it together. I'm going to essentially be able to put this whole thing together, then work on the tuning, then work on the actual ROS navigation stack, work on computer vision, get all that done separately while being able to still easily access all the electronics. So that's the goal. And yeah, I'm looking forward to this project, and hopefully the next video we're going to order these parts and actually get assembling, get building. So by the end of the next video, we should have the full actual frame of the Segway put together. Okay, so I hope you enjoyed the first of what will be several videos about the open source Segway build. If you enjoyed the video, do me a huge favor. You hear it on every video you'll probably ever watch on YouTube. Like and subscribe. Those subscriptions are super helpful, and they really, really motivate me to keep doing builds like this. I've got a lot of cool stuff built into the future that I really want to do, and I kind of need your help to get there. So thank you so much. Look forward to the next video. Bye, guys.